Welcome to the session on the PIEVC protocols. In this video, we'll talk about the original PIEVC protocol as well as the PIEVC green protocol. In this module, we will strengthen our understanding of ecosystem-based adaptation and ecosystem services, and how natural systems contribute to climate resilience. We will then explore systems thinking, recognizing that infrastructure operates within interconnected social, environmental, and technical systems. We will examine the PIEVC family of resources, including the core PIEVC protocol and the PIEVC green protocol, and discuss their role in climate risk assessment. We will also develop the ability to apply the impact chain approach to systematically analyze vulnerabilities in infrastructure systems. We will deepen our understanding of the PIEVC green methodology for integrating nature-based solutions into climate risk assessments. Let's begin by exploring ecosystem-based adaptation and ecosystem services. Ecosystem-based adaptation, or EBA, bridges environmental protection with climate resilience strategies. EBA is defined as the use of biodiversity and ecosystem services as part of an overall adaptation strategy to help people adapt to the adverse effects of climate change. This definition comes from the Convention on Biological Diversity in 2009. In essence, instead of relying solely on engineered or gray infrastructure solutions, EBA uses nature itself, forests, wetlands, mangroves, green spaces, as buffers against climate risks like floods, heat waves, or droughts. EBA is not just an environmental tool. It has cross-sector relevance and multiple co-benefits. It's cost-effective, particularly for lower income and climate vulnerable regions. It generates co-benefits like improved public health, additional income opportunities such as through ecotourism or sustainable agriculture, and ecosystem services like water purification, carbon storage, pollination, and recreational value. EBA also contributes to biodiversity conservation, protecting both ecosystems and the livelihoods they support. Globally, ecosystem-based adaptation is being increasingly mainstreamed into policies and climate planning, especially within frameworks for climate change adaptation and disaster risk reduction. To summarize, EBA is a nature-centered approach that not only helps us adapt to climate change, but also brings a suite of social, economic, and ecological benefits. It's holistic, scalable, and essential for sustainable development. This slide explains the relationship between ecosystem-based adaptation and the broader concept of nature-based solutions, particularly in the context of climate resilience. Nature-based solutions. These are defined as actions to protect, conserve, restore, sustainably use and manage natural or modified terrestrial, freshwater, coastal, and marine ecosystems, which address social, economic, and environmental challenges effectively and adaptively while delivering human well-being, ecosystem services, resilience, and biodiversity benefits. Ecosystem-based adaptation is a pillar of nature-based solutions. Within nature-based solutions, ecosystem-based adaptation is a more specific subcategory that's focused on climate change adaptation. Ecosystem-based disaster risk reduction, the sustainable management, conservation, and restoration of ecosystems to reduce disaster risk with the aim to achieve sustainable and resilient development. Ecosystem-based disaster risk reduction is depicted as being only partially within the term nature-based solutions for adaptation. as eco-DRR can also refer to activities and approaches that address non-climate disaster risk, such as tsunamis and earthquakes. As ecosystem-based adaptation refers to ecosystem-based approaches to climate change adaptation, it is entirely situated within the scope of nature-based solutions for adaptation. Ecosystem-based adaptation is considered a type of nature-based solution, specifically for climate change adaptation. In the PIEVC Green Protocol, the term EBA is used to emphasize climate resilience. This slide demonstrates how ecosystem-based adaptation can be applied to strengthen climate resilience in water-related infrastructure. Rather than relying solely on gray infrastructure like dams and pipelines, ecosystem-based adaptation offers an integrated approach that either supports, enhances, or substitutes these systems using nature-based strategies. On the left side of the screen, climate-proofing actions. The four key EBA actions shown on the left are protect, replace, assist, and accompany. These represent different ways in which ecosystems can contribute to climate-proofing infrastructure. The middle column, infrastructure targets. Ecosystem-based interventions can be directed toward a wide range of water infrastructure, including dams, reservoirs, irrigation canals, and water supply pipes, wastewater treatment plants, wells, cisterns, desalination systems, and more. If we look to the right-hand side, infrastructure services, these systems can provide critical services such as flood control, water supply reliability, erosion control, hydropower generation, and even navigation and transport. Ecosystem-based adaptation supports these services by enhancing performance and resilience to climate stress. This framework helps us rethink water infrastructure, not as isolated engineered systems, but as part of a broader social and ecological system. By integrating ecosystem-based adaptation, we gain not only resilience, but also social and environmental co-benefits, an essential shift for climate adaptive planning. This slide illustrates the spectrum of infrastructure solutions that combine the strength of both nature-based and engineered or gray systems. These hybrid approaches are especially valuable for climate adaptation, water management, and disaster resilience. From green to gray, ecosystem-based adaptation can be combined with traditional gray or engineered infrastructure. This combination creates green-gray infrastructure, or also hybrid infrastructure. It represents a spectrum of solutions that blend nature-based solutions with physical infrastructure. An important consideration is that hybrid infrastructure may also be vulnerable to climate change impacts and requires climate risk assessment and resilience planning. This table shows a wide range of functions and benefits provided by different types of green infrastructure. It helps us visualize how each intervention can support climate resilience, water management, biodiversity, and other co-benefits, either as a primary or a secondary function. Let's take a look at a few examples. Green roofs, commonly used in urban buildings, primarily to help reduce stormwater runoff and increase energy savings, while also offering secondary benefits like a visual amenity or even biodiversity habitat. Rainwater harvesting systems are focused on water saving and recycling and stormwater storage, making them key tools in water-scarce regions. If we look at landscape-based solutions, we see that constructed wetlands and bioswales are multifunctional. They reduce runoff, filter pollutants, support biodiversity, and provide amenity values. Permeable pavements and rain gardens are also widely used for both stormwater management and improving water quality through infiltration. This table reinforces the idea that green infrastructure can deliver multiple layered benefits, making it a smart investment for sustainable urban planning. It not only addresses immediate infrastructure needs, but also improves public health, environmental quality, and climate resilience. This slide introduces a new term, ecosystem services. These are the benefits that people obtain from nature. Ecosystem services are grouped into 4 categories, and it's important to understand the role each one plays in supporting human and environmental well-being. Let's start at the base of the triangle. Provisioning services are the tangible goods we get from ecosystems, like food, water, fiber, fuel, and medicine. These are the most visible and often the most economically valued services because they're directly extracted and used. Regulating services refer to the natural processes ecosystems perform to help control environmental conditions. Think about things like climate regulation, flood prevention, air and water purification, and pollination. These are often underappreciated until they fail or are disrupted. Cultural services are the non-material benefits ecosystems provide, such as recreation, spiritual connection, aesthetic enjoyment, and cultural identity. These support the mental and emotional well-being and are deeply connected to cultural heritage. And at the top, we have supporting services, which are foundational. These include nutrient cycling, water cycling, photosynthesis, and soil formation, all the background systems that enable the other 3 categories to exist and function. The reason we include this framework is to remind us that when we're assessing climate risk or developing infrastructure projects, we need to consider not just engineered systems, but also the ecosystems that support and protect our communities. As we move into the next sections, we'd like you to keep this framework in mind. When we integrate ecosystem services into infrastructure planning, we begin by recognizing the different types of ecosystem services that are provided: provisioning, regulating, supporting, or habitat, and cultural services. Among these regulating services, such as flood control, water regulation, and temperature moderation, are particularly important for climate risk reduction. These services are central to ecosystem-based adaptation as they enhance resilience while maintaining ecological integrity. Mapping ecosystem services help to identify critical natural assets that can strengthen infrastructure performance and reduce vulnerability. When we integrate these insights into planning, infrastructure is no longer viewed in isolation, but as part of a broader social and ecological system, supporting more sustainable and adaptive decision-making. Systems thinking is at the foundation of building climate resilience, especially when we are addressing infrastructure and ecosystem planning. Rather than treating infrastructure systems separately from nature or society, systems thinking views them as interdependent. This approach recognizes that solutions must consider the complex interactions between people, ecosystems, and the built environment. It also emphasizes that humans are part of nature, not separate from it, shaping and being shaped by ecological systems. So what do we mean when we refer to social ecological systems? Social ecological systems consider the local environment and how it is being impacted by external factors, as well as the local people and how their practices and institutions interact with the environment. This in turn is, of course, impacted by factors beyond the local level, making these systems quite complex. We are interested in each of those elements of the social ecological system that have an impact on climate risk of our infrastructure. For example, if people are accustomed to throwing waste in drainage canals, this can negatively impact the risk of flooding. On the other hand, considering the environment, urban greenery may positively impact both heat and flood-related risks. Generally, using systems thinking allows us to think about how the social ecological system within which the infrastructure project is located may interact with the infrastructure itself. It can reduce risks, for example, vegetation on a slope, which reduces the risk of landslides that would lead to road interruptions or infrastructure damage. It could increase risks. For example, if mangrove forests are degraded, they provide less protection, for instance, from heavy winds and storm surge, to the coastal infrastructure behind them. On the other hand, if the risks to the infrastructure are realized, this may impact the social ecological system. Here an example is if a water treatment plant is flooded, which could lead to water pollution downstream. So how do we apply this approach? The PIEVC Green Protocol uses impact chains and vulnerability indicators to identify risk drivers as well as potentials for risk reduction beyond the infrastructure system itself. The PIEVC protocol is an approach to assess climate risks to infrastructure. We'll first talk about the PIEVC protocol, and then later we'll address and discuss the PIEVC Green Protocol, which looks at social and ecological systems. This slide illustrates the evolution from the original PIEVC protocol to the more holistic PIEVC Green Protocol. The original PIEVC protocol has been a foundational tool for assessing climate risks to infrastructure. It provides a structured, step-by-step methodology for understanding how climate change may affect the performance of infrastructure systems. This protocol has been tested and widely used internationally. However, as our understanding of climate resilience has evolved, so too has our need to take a systems thinking approach. This means we're now able to look beyond the individual assets to consider how infrastructure interacts with broader social, ecological, and governance systems. The next part is adding the integration of ecosystem-based adaptation into the risk assessment process. This adds a nature-based dimension to the protocol, acknowledging that ecosystems themselves can serve as infrastructure and offer co-benefits such as water retention, temperature regulation, and biodiversity. PIEVC Green Protocol is the result of this integration. It retains the core technical structure of PIEVC, but expands it to recognize nature as a key adaptation asset, promote multi-sectoral collaboration, and to support sustainable, resilient, and inclusive decision-making. So essentially, PIEVC Green is the original PIEVC protocol layered with systems thinking and ecosystem-based adaptation. It's an enhanced tool that supports both engineered and nature-based solutions in adaptation planning. The PIEVC Green Protocol evolved from two key foundations. On the left, we see the GIZ Ecosystem-Based Adaptation Climate Risk Assessment Guide. It brings systems thinking, and ecosystem-based adaptation, treating ecosystems as part of the solution. And on the right, the PIEVC protocol. It retains 5 core steps of the original PIEVC protocol and adds a triple bottom line lens to capture social, environmental, and economic impacts. These two sources and processes and the lessons learned from them are integrated together into the PIEVC Green to create a more integrated, climate and nature-focused version of the protocol for assessing infrastructure resilience. This table summarizes some of the key differences between the original PIEVC protocol and the newer PIEVC Green, highlighting how the approach has evolved to meet broader and more integrated climate resilience needs. The PIEVC Green expands the scope beyond the infrastructure to include social and ecological systems and landscape level resilience. PIEVC Green integrates nature-based solutions like ecosystem-based adaptation. The terminology and methods have been updated to align with the Intergovernmental Panel on Climate Change 6th Assessment Report, or AR6, making it current and relevant and aligned with other documents that are in use internationally. The structure of PIEVC Green is unified and streamlined, making it easier to use, particularly for non-engineers. The original protocol focuses on technical infrastructure risk. PIEVC Green takes a systems thinking approach, emphasizing co-benefits and global applicability.
Welcome to this e-learning session. In this video, we will focus on the PIEVC Green. This guide builds on the core PIEVC methodology and other resources, including the PIEVC High-Level Screening Guide. PIEVC Green was created in 2022 to respond to the growing need of practitioners. The PIEVC Green takes the infrastructure lens and the core steps from the PIEVC when we refer to social ecological systems. Social ecological systems. What do we mean when we refer to a systems thinking approach? Broadly speaking, when should you use the PIEVC Green compared to other? When you apply PIEVC Green, thinking about the scope of your. Moving on to step 2. In the PIEVC protocol, this is data. Impact chains are a unique feature of PIEVC Green that you won't see. Let's look at a more detailed version of the example we just used to explain. Once you have developed your vulnerability indicators, this allows you to perform both step 4, the optional engineering analysis, and step 5. Step 6 to 8 is used to identify and assess adaptation options. In summary, the PIEVC Green is a resource to help support. Thank you for listening to this e-learning session. You can also find out more